This is an introduction to Maxwell's equations, as per AP Physics C, Electricity and Magnetism. To follow through Maxwell's equations, you need to have a strong understanding of the concept of flux. Flux describes the flow of energy through a surface. In electronics, specifically, we're talking about an electric field and a magnetic field. We draw flux like we draw field lines, and we look at the cross-sectional area of the plane in the neighborhood of electric charges or magnetic poles. So here's the electric field, and we can look at the electric flux through this plane, that plane, or the other plane. Similarly, we can look at the flux through a magnetic field at any point in the plane, just like we did when that plane was. Now, quick review of the gradient operator from first semester when we played around with this with potentials and conservative forces. The gradient, upside down delta, sometimes called ATLED, A-T-L-E-D, delta backwards, sometimes called nabla, because this upside down triangle looks like the kind of navel, the kind of Mediterranean or Greek harp seen on urns and in Tehillim. That grad is rate of change in the x direction, x, rate of change in the y direction, y, rate of change in the z direction, z. It's a vector operator. The gradient is supposed to give you the three-dimensional contours of the surface you're working on. Notice it's kind of weird to say slope because the surface or the vector field can have different rates of change in different directions. This is a three-dimensional version of reading those potential graphs that we did in the fall when we did conservative forces. Look at the grad, look at the gradient, put a negative sign in front of it. That's the way the ball is going to roll if you put that ball down on the three-dimensional surface. It may roll across, over to the left, up, and back. 3 different dimensions of slope. And it doesn't have to be slope either. The most common place you've heard the word gradient is probably the temperature gradient. As you explore a given surface, what happens to the temperature you're on? Now that we've got the operator down, let's use that operator in the dot product and cross product to tell us things about the system, full of iron filings. Now let's learn some new operators. Dabble some more in multivariable calculus after you already learned in AP Physics that you can take a derivative with respect to x, with respect to y, with respect to z, and the process works the same for all 3, keeping the other 2 variables you're not working with as constant. Remember that upside down delta? This is the upside down delta. Let's start with the idea of divergence. Divergence starts with a vector and gives you a scalar. What does it measure? It measures how much flux is entering or leaving that part of the system that you're working on. It's flux per unit volume, or flux density. Now, if you're doing divergence correctly, if you have a source of charge, if you have a sink into which the charge is going, the sum of the sources minus the sum of the sinks should give you the net volume of flow out of the system. Let's see how that works. This is a system with 0 divergence. Flow in equals flow out. This is a system with positive divergence. Everything is flowing out. This is a system with negative divergence. Everything is flowing in. When you're studying field lines, you can look at the map, as we called it, and you can see divergence and work it out graphically. So, the divergence of the vector field measures flow per unit volume. Sorry about the bad graphics. This was supposed to be a dot product, but it didn't show up on the screen. It's the vector operator del dot A. So here's our divergence. Let's take the dot product, ddx in the x direction, dot ddy in the y direction, dot ddz in the z direction. Remember, because of the dot product, this is a scalar product. The divergence shows the rate of change of the vector in the x net y, net z, the whole rate of change of the entire system. Given that this is a gradient operator here, this will tell you the net flow into the system or out of the system. If you've got one source and one sink, then the net flow into and out of your system should be 0. If the net flow is positive, you should have a single, an odd number, some kind of source of charge there. If the divergence is the dot product, then the curl is the cross product. Set up your square to take the cross product of two vectors. The first one, your atlet, your nablet, ddx, ddy, ddz, and the second one, your vector you're finding the curl of. Take the cross product. Again, 3 diagonals, 1, 2, 3, minus the other 3 diagonals, 1, 2, 3. You can see rate of change in y and z in the x direction, rate of change of z and x in the y direction, rate of change of x and y in the z direction, and there is your curl. The curl is the vector operator that describes the rotation of the vector field. At every point of that field, you can see the curl of that point that characterizes the rotation. Again, like all rotational quantities, right-hand rule gives you the direction of that curl. The curl is going to give you the angular velocity or rotation of whatever system you're looking at about that point. Now that we're clear on the operators and what they mean, let's get into Maxwell's equations. Thanks to the Brazilians for the nice slides. James Clerk Maxwell was a Scotch scientist who began at the University of Edinburgh and worked a good deal at Cambridge in his later years. In 1865, he knew he was onto something when all of his calculations pointed to the idea that electromagnetic waves travel at what was then known as the speed of light. This discovery laid the foundation for Maxwell's exploration of the relationship between different electromagnetic waves and how that relationship could be explained with calculus. His 4 equations sum up everything we know about electromagnetism and are the foundation for the dawn of 20th century physics. He also had a good deal to say about religion, which if we want to look up on the Wikipedia, has some primary sources and some pretty good quotes. Maxwell's equations represent a huge body of work that was completed separately at different times in different places. We can thank Oliver Heaviside for summarizing all of Maxwell's work in precisely 4 equations. Maxwell's equations can be represented as derivatives or integrals. Let's cover our bases and do both. Maxwell's equations summarize everything we know about the interaction between electricity and magnetism, the fact that electric charges create electric fields, moving charges create magnetic fields, and changing magnetic fields create electric fields. Please note the difference between the magnetic field H with B, the magnetic field we've been studying here too. This has a constant of the magnetic permeability of free space, which changes the units. Let's take a look. Maxwell's first law says that if you draw a closed surface, imagine it like a sphere, or if you're getting really complicated, like a blob, the flux of the electric field in that space is directly proportional to the electric charge within that space. Or as we said, first year in high school physics, the stronger the charge, the higher the electric field. The weaker the charge, the lower the electric field. Now, let's take a look at it with the grad here. Let's take a look at the divergence. The electric field diverges from positive charge, field lines go out, and converges to negative charges, field lines go in. This is the rule we cited again our first year in the classroom, that field lines move away from positive charges towards negative charges. Quick tour of the calculus here. This is a closed surface integral. You can't just make the starting and ending places wherever you want. Your path has to be a closed path around the whole surface. check, make sure you've got vectors and direction. What's the direction? This is flux. The direction is flow perpendicular to the surface, and having done that, then you can do dA, dx dy in Cartesian coordinates, or in cylindrical coordinates, or in spherical coordinates. Honestly, if our area is a sphere, we're going to be doing this in spherical coordinates a lot. What do you get? Your charge, Q, they're going to write Q enclosed for short, only the enclosed charge. If your system has one charge inside that sphere of influence, there may be a dozen others, but it's not going to be contributing to this calculus inside that sphere of influence. What is going to be contributing is the electric permittivity of free space. Remember, we said Coulomb's constant was not so constant? This is what's constant if you're in a vacuum. If you're not in a vacuum, then this is not going to be the electric permittivity of free space. It's going to be the electric permittivity of whatever your material is. Now, in differential form, we're going to take dx, dy, dz, dot product electric field. We're going to find the change in the electric field in the x direction, dx, and the y direction, dy, and the z direction, dz. We're going to add them up to find the divergence, and that divergence is going to be the charge density in coulombs per cubic meter, again, over the electric permittivity of free space. This is sometimes called Gauss's law. It certainly is in the first section of AP Physics C, Electricity and Magnetism, or second quarter college physics for scientists and engineers, where basically this is the equivalent of fraternity hazing for a physics major. You have to pay your dues, do 2 weeks on Gauss's law until you never want to see it again. You're so sick of these integrals before you can move on. Now, let's move on. Swell, another one of Gauss's laws. A real bright guy, Carl Friedrich Gauss. Second of Maxwell's equations. Let's try this again for magnetic fields. We know there's no such thing as an individual magnetic charge. There's just no such thing. Magnetic fields are only created by changing electric fields. So take a look. There's no magnetic charge on the right side. The total magnetic flux passing through any closed surface is 0. You will have field lines diverging from the north and converging on the south. No matter where you are, you can be enclosing the north and south poles, or you can just be looking around north, but I guarantee that those field lines will be pointing this way, coming away from the north, and pointing this way, coming toward the south. There's no surface you can draw that won't have both of them, and so in the differential form, there you see on the right-hand side, again, the divergence of the magnetic field at any point is going to be 0. Again, tour of the calculus, you're taking a surface integral, an integral over a closed surface. So if you're doing d theta, that would go from 0 to 2 pi. If you're doing d phi, in 3 dimensions, it would go from 0 all the way around to pi to twirl around to make your sphere. This is B, the magnetic field vector. Notice you've got that magnetic permittivity of free space in the denominator that doesn't appear here. Again, we're looking at the direction of the flux through the surface, normal to the surface. Then you can do dA in any units you like. R sine theta, dr d theta, if you're in cylindrical coordinates, which are usually the easiest to work with. And in the differential form, again, you're taking the gradient dot h. You're finding the divergence of h, the magnetic field, in amperes per meter. All right, 2 down and 2 to go. 6 minutes and 12 seconds later, we are done with Maxwell's first 2 equations, and we are on equation number 3, which comes from Faraday's law. We talked about Faraday's law a little bit in one dimension when we were defining electromagnetism our first year in the classroom. Check it out. Here is your magnetic flux, B, dA, perpendicular to the surface, and here's that magnetic flux changing over time. A changing magnetic flux introduces a voltage. And remember, this was one of our original equations for voltage. We said that electric potential energy was QE dot change in displacement, and potential, which was to say voltage, was electric potential energy per unit charge. So we lost the Q, and we can't say dd, that's just silly, and we can't say dx because there's no rule that your battery has to be facing this way. For all you know, it may be an AC source that's constantly spinning. So this is a line integral here. You'll see that in a minute. And changing your magnetic field will create an electric field in that direction, opposite to that change in magnetic field. You'll see this in differential form. Here is the curl of the electric field. What's the curl? It's negative dB dt, opposite of the change in the magnetic field over time, such that the currents induced by changing magnetic flux always flow in the direction so as to oppose the change in flux. This is what we said last year. The new field tries to return the system to its original state. We called it sort of like electromagnetic inertia. So again, let's tour the calculus. Here is our line integral. Sum up those contributions from each portion of the closed path. We're talking a model that looks like non-conservative forces here, from here to here to here to here to here to here. That done, find your voltage, find your electric potential, your electric field, dot dl. We used to call this ds when we were doing center of mass and moment of inertia, but you've got a path, and there's an equation for that path. It could be a weird sort of curvy path. It could be a circle, could be a box, but either way, a box has four sides. Break each side down and do it separately. dl, here, 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 and here. Find that total, because if it's there, that's going to induce a changing magnetic field. Electric field that changes over space will, over time, change the magnetic induction, B dot dA. The curl of the field is going to involve a change in magnetic field over time. And if that field curls, it will change the magnetic field, just as if the magnetic field changes, that will change the electric field. Changing electric fields creates
magnetic field.
And a changing magnetic fields creates electric fields.
Yep.
Next question is how much? Now we have Ampere's law as integrated with Maxwell's own work. Fourth and last of Maxwell's equations, the Ampere-Maxwell law. Let's take a look. Again, we're going to have this line integral here, dl. If you take the line integral all the way around with the magnetic field, notice that this is C for circulating. That is going to be equal to the current enclosed by that line plus the change in electric flux over time times the electric permittivity of free space. That's how much your magnetic field is going to change. And this brings us back to what we wrote on the board the very first day we discovered electromagnetism with the wires and the batteries and the compass needles. In our class, we say changing electric fields create magnetic fields. But I also put on the board what everybody else's textbook and PowerPoint presentation says, which is moving electric charges create magnetic fields. The Ampere-Maxwell law has them both. This is a term for moving charges, or as we call it our first year in physics, electric current. And this one is a separate term for your changing electric field over time. If you do this in differential form, now let's take a look at the curl of the magnetic field. The curl of the magnetic field is produced by an electric current. Capital J is the vector form of I. I know it's crazy, but I is the magnitude of the current, and J is the magnitude of the current in the direction of the wire. There's your vector direction for J. See, it changes at every point along the black path. Quick tour of the calculus again. Here is, again, dl going round that closed path in a direction given by the right-hand rule. Brilliant Brazilian professor Bruno Larissa made this when he was a student, and English was not his first language. Let's give him an A+ for physics. Again, we're talking H in amperes per meter, closely related to B, the magnetic field that we've been looking at, and the magnetic permeability of free space. Only the current enclosed by your line. So in physics for scientists and engineers, you're going to have your wire running this way, and you're going to draw a nice little dotted line around that wire. Say, doot, 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 doot. All right, there's my path. It's a closed path. Theta goes to 2 pi. The wire goes straight through the middle of it. Nice cylindrical geometry. And there's the current enclosed. It's whatever's flowing through the wire. And again, we're looking at the electric permittivity of free space and the electric flux through any surface bounded by that line. If the only thing that's in your little dotted circle is a wire, you're good to go. But if you've got charges there with field lines, you'll take that into account too. Again, let's take a look at the curl of H, our magnetic fields in A over M. Current density, there's that vector we were talking about. This is amperes per square meter. This is the change in electric field over time, as we were talking about before. There you have it, all of electricity and magnetism in 4 short equations. It is a beautiful thing. Electric flux, electric fields are caused by electric charges. Magnetic flux, magnetic fields are not caused by magnetic charges. They are only caused by changing electric fields, and what goes out must come in eventually. How are they caused? This is how, and this is how big those magnetic fields will be, and this is how big the changing electric fields will be that were caused by the magnetic fields. Thanks again to Bruno Larissa Lima Cristomo for the slides, and best of luck as you move on in E&M.